In this video, I'll be discussing the third lab in Physics 2212 on the behavior of simple circuits. Introduction. This lab modeled two simple circuits in the PhET circuit construction kit to evaluate the relationships between current, electrical potential, and the effects of resistors and capacitors. These models were then compared to the real-world circuit behavior. Circuit 1. On screen is Circuit 1, comprised of two batteries and two resistors of 47 and 100 ohms respectively. First, the current was predicted using Kirchhoff's rules and assuming zero wire resistance to get that I1 and I2 both approximately 0.02 amperes, which was then confirmed using the PhET model. Reversing the ammeter did not change the magnitude of the current reading. Removing one of the ammeters and connecting the open circuit to the voltmeter, we see that the remaining ammeter reads 0 amperes while the voltmeter reads 3 volts. Since no current flows through an open circuit for 0 amps, and since the 3 volt electromotive force of the batteries is unimpeded by resistance without the presence of current by Ohm's law. Closing the circuit, we can now use the voltmeter to measure the electric potential between each of the circuit's components all the way around the circuit. By Kirchhoff's voltage law or loop rule, the sum of the electric potential readings from each section around the circuit should equal 0, which is exactly what we see when we add the recorded values together. We can also display the potential change as a function of position within the circuit, as seen on screen. Now, when we connect the voltmeter, we should note that the voltmeter becomes part of the circuit. By Kirchhoff's loop rule, more of the current passes to the side of the parallel circuit with less resistance, and since an ideal voltmeter has infinite resistance, negligible current flows through the voltmeter. Thus, by Kirchhoff's node rule, the current through the voltmeter is negligible, thus leaving the ammeter reading unchanged as a matter of the current through the resistor. However, if we are to connect an ammeter parallel with a 100 ohm resistor, the current flowing through the circuit does change. Since an ideal ammeter has 0 resistance, most of the current flows through the ammeter, effectively negating the effect of the 100 ohm resistor on the current. Thus, the total resistance decreases and the current reading increases to 0.06 amperes. If we go back to the original circuit, we can calculate the resistance of each component by dividing the electric potential over the component divided by the current flowing through it. In this case, the calculated values for the wire and the ammeter are 0 since there was no potential difference, but the calculated resistance for the resistors differs somewhat from the nominal values of the resistors, as displayed on screen. Circuit 2 is a simple RC circuit consisting of a 9-volt battery, a light-up bulb of 10 and 20 ohms, and a 200 millifarad capacitor. As the three were connected, the light bulb first lit up and then dimmed as the capacitor charged. Then, by disconnecting the battery and closing the circuit yet again, the bulb lit up and dimmed as the capacitor discharged. Displayed are the charge and discharge times measured for both the 10 and 20 ohm light bulbs. Next, a new circuit with a 30 ohm bulb was charged and then discharged while tracking the electric potential of the capacitor over a 20-second period. The data was then linearized and used to determine the calculated value for the time constant RC. The calculated RC constant differed by about 0.48 seconds from the modeled value, where the potential difference was 1 over E of the original potential, as displayed on screen. Discussion. This experiment was completely digital, which minimized any potential for error. The only area that could have been affected is the digital timer readings for the capacitor's discharge electric potential over time. What if questions? What if this experiment were performed in real life with an actual ammeter? In this scenario, the real ammeter would have a non-zero resistance, which would in turn add resistance to the circuit and contribute to more voltage drop, decreasing the overall current in the circuit. What if, in real life, you used a real battery to charge a capacitor with no resistor in the circuit? Without a resistor, the capacitor would charge rather quickly since RC would be very low. However, in the model, the capacitor would charge instantaneously since zero resistance would impede the infinite current, and RC would be equal to 0. However, in real life, resistance would come from both the wires and the internal resistance of the battery, thus resulting in the non-instantaneous charging of the capacitor. Conclusions. In conclusion, this lab provided a deeper understanding of the relationship between current and electric potential, the charging and discharging of capacitors, and the tools used to evaluate electric circuits. Thank you.